Velkommen til et nyt webinar. Som altid har jeg jo en gæst med i studiet, og denne gang har jeg været så heldig at få professor Arcavi ved min side, som kommer fra Weizmann Institute i Israel. Arcavi er internationalt kendt for sin matematikdidaktiske viden omkring begrebet symbol sense, i forlængelse af begrebet number sense. Symbol sense det refererer til en dybere forståelse og til intuitive evner, der kræves for at arbejde med symbolske repræsentationer. Men det kommer vi alle sammen til at høre lidt mere om et øjeblik. Som sædvanligt får Arcavi de næste cirka 30 minutter til sit oplæg, og derefter holder vi en kort pause på et par minutter, og så vil Arcavi og jeg føre en samtale om det oplæg, han har præsteret, så vi ses. And now, welcome to you, Abraham, and thank you for taking your time to visit Denmark. We are very happy to have you. I've just introduced you for the viewers, and then I will ask you for start your presentation.
So, thank you very much for having me here. It's a great honor and a great pleasure to be here. And I wish I could speak Danish, but we'll have to do it in English. I hope it will be clear, and if not, you will tell me. So the topic, as Bent has said already, is number sense and symbol sense, topics that I was working for quite some time. And I will share with you some of the basic ideas behind these two topics. And then if there is issues that are left to discuss, we can certainly discuss them. So let's get started. Number sense, as you can see in this slide, was the object of much discussion in the 1980s, especially in the United States. And it was some kind of a reaction against what was in the 70s, the back to basics, which was a reaction to the new math. So the back to basics was a movement that the premise was, let's go back to numbers and operations because students don't know how to do addition and multiplication, the multiplication table. So much emphasis was placed on operations, and the number sense movement came as a way of saying this is not enough in order to become acquainted with mathematics. The caricature that was that expresses most of it can be found in an old book. Let's see this exercise, and you can say, as the guy here, oh my God, look at the terrible exercises, and you have find two characteristics. This is more a caricature because I don't think nobody faced, even in the 70s, these kind of things. But you have here not only very large numbers, but also very complicated operations. And this is certainly not a good idea, certainly not nowadays when we have calculating machines that can do complicated. So the emphasis was placed on number sense. Look at this, for example. This is an exercise that one of the ideas of number sense is to want children to see this, and instead of jumping to find the common denominator, look at that these two numbers are very close to 1, so the sum would be very close to 2. And you want them to have this sense of just looking at something and communicating with the underlying idea, sense of magnitude of the numbers, not rather than calculating. You can calculate, but ahead of calculating, you can have a sense of what you are expecting that this procedure to. So this is just one component of number sense. Another component of number sense would be, suppose you have to perform this operation. And instead of doing the long way, you can say, okay, let's take the liberty of transforming the second number into twice as much, and then into twice as much, and then become an operation that you do have to solve without much procedural effort, and then you have to readjust in order to have the original result. But what you do, multiplied by 2, so in fact you multiply by 4, now you have to divide by 4, and then you can have your result. So a second component of number sense would be have the idea that you have the autonomy to recompose operations in a way that make the calculations more easy for you and more friendly for you. So that's another component of number sense, understanding that you have this liberty. Here is another way that 15 times 14, 15 times 10, and 15 times 4 you can decompose, because you know there is an underlying property of distributivity. And but then you have the limitations of distributivity. You have the extended distributivity of things you cannot do, for example, because so the underlying properties of the structures of how properties can be handled. So that's the second component of number sense. A third component of number sense, what you see here is an item that we, in Hebrew, that is translated into English. This is a questions we administer to second graders in Israel in order to see whether the exercise says, can you put the sign greater than or smaller than, and is it possible to answer the question without, sorry for the typo, without calculations. The idea was somehow related to what Caroline Kieran in webinar series talked about structural thinking. They see the structure, and they see the same number being subtracted by two numbers, and then to see how many kids can produce this answer, which is, since 13 is smaller than 25, it takes away less. So if you take away less, the number in the left-hand side should be greater than the number in the right-hand side. So it's reading behind the operation, reading the structure, what Caroline Kieran called structural thinking. So that's another aspect of number sense. Another aspect of number sense is here is an interesting operation, and it has a surprising result. It has a surprising result, 1/8. And you can have several ways of doing it. Well, the traditional way is finding common denominator, and that's the traditional way of finding it. But then you can ask for alternative ways of doing it. And then, since I mentioned properties, another way of doing it could be this one. For example, extracting 1/9 as the common factor, and then 1 plus 1/8, and then it becomes an interesting way of simplifying, and then you get the 1/8. So the idea of flexible ways of doing an operation in order to apply properties and see structure. And suddenly, look at this funny thing of doing this, another way. You can make the observation that if you have the courage to replace the multiplication by the minus, you have 1/8. Wow, this is magic. But you can replace multiplication by subtraction everywhere. But there are cases in which the multiplication of two numbers can be the same, can have the same result as the subtraction of two numbers. Then the question, interesting mathematical question from a simple calculation that arises, when is that possible? And that you can lift to levels of doing algebra, find two numbers that the multiplication is equal to their subtraction. And this is an interesting exercise arising from a simple calculation. So you have a simple calculation, and instead of doing the caricature of with big numbers and lots of calculations from one exercise, you can look at different ways and derive interesting properties and work with them. And then you say, but these are in a sense, technical manipulations that you do to numbers. Is there a way that I can have some sense or some feeling in my guts about what's going on with these numbers? So then you have, you can propose a way in which you connect better than with formal procedures, even if you are proficient with formal procedures. And let's represent, for example, this is 1/9. And this is 1/8 of 1/9, right? So you take 1/9, and on one of the ninths, the other ninths, you divide it into 8. So what do you have here? You have 1/9 plus 1/8 of 1/9. So look at the picture and see that now you have the left-hand side, 1 square plus 1 triangle. But then you can see the right-hand side by looking that there are 8 combinations of a square and a triangle. 8 combinations of a square and a triangle, so the sum is 1/8 of the total. So I think that the ability of having another representation, or if you want, as Duval called it, register, you can have a feeling of what's the operation here and make say, aha. And you know these pictures in which you have a princess and a lady an old lady that depending on where you fix your eyes, you see one or see the other. I think here you have a similar situation. If you can see the left-hand side as the sum of 2 things, and you can see the right-hand side as the whole, as a part of a whole. So you can have 2 things, and this is an interesting. So this is also could be also a component of what I call symbol sense, and in this case you do operations, but you impose of them the need for some meaning. Numbers in context. The country of Belgium. These are data that I took from the internet and I just approximated and rounded up. And these are 2 countries. Well, Iceland is almost 3 times bigger than Belgium, but look at the population. Very interesting numbers. So having numbers in context, what is a large number depends on where is it applied in comparison to others. And then the need for making a different quantity that expresses something different than these numbers, which is the density. And the need of seeing the numbers in context, that you can operate with them in order to have a sense of how the numbers in context are expressing the magnitudes. Is 400,000 a big number? Well, if you look at the distance from the Earth to the Moon, which is 300,000, it's not a big number, because in universal terms, it's a millimeter. But if you look at the distance, how many times you can go around the Earth with 400 kilometers, 1,000 kilometers, it's a large number. So seeing the number and the magnitude, the order of magnitude, depends on context, and applying numbers to context is another aspect of having a sense of numbers. So there are many more aspects to number sense, but let's summarize. Recognizing orders of magnitude and estimating. Relating arithmetical properties with calculations, and this is the example I gave. Capturing the essence of operations is the bigger than. Representation of numerical phenomena, we have that example. And then numbers in context, we have that example. These are just some of the issues that I mentioned on number sense, but this can be extended to other situations as well. But now you can have the idea that number sense is a non-algorithmic field for numbers. It's a sound understanding of their nature and the nature of the operation. What does an operation do? Like make it bigger, make it smaller when you subtract, when you multiply. A need to examine the reasonableness of a result. A sense of the relative effects of operating with numbers. A feel of orders of magnitudes and estimate. And the freedom to reinvent ways of operating with numbers differently from the mechanical repetition of what was taught and memorized. That's the example of the 13 divided by 3.25. So these are some of the issues that I was trying to convey, that are the ideas that behind the idea of number sense that goes beyond just procedural calculation. That doesn't mean that you have to abandon procedural, because the procedural and the sense, they should go hand in hand. Okay, in sum, I would say in a very simplistic definition, if you will, to feel at home with and to interact meaningfully with number situations at home, at work, in school. So it transcends the idea of having numbers in school environments. It goes beyond that when you go up to work and when you go up to the supermarket to buy things and you compare prices, for example. So it includes knowledge of facts, skills, strategies. It includes attitudes to knowledge, namely that I can be the boss of my calculation. And agency means I am autonomous. It's not that I'm repeating or doing exactly what the teacher wants from me. I can put my hands on it and try to do other things. And it includes the idea of being inquisitive, meanings curious to do what if not. It's an attitude to knowledge. It's not just being critical to what others say. And thinking habits. And what is the thinking habit? It includes observing, because many things comes from just deep observation. Questioning, what if not. Looking for connections. Checking and revisiting. The 1/8 example, for example, is checking with different ways of operating. So, what about symbol sense? So the idea of number sense was very popular, as I said, of number sense was very popular, as I said, in the 80s. And then the idea was, okay, can we extrapolate the idea of number sense to symbol sense? Because arithmetic has one characteristic and algebra has a different characteristic. And algebra is also something that is a stumbling block for many students. So symbol sense, and here are some of the characteristics that I try to describe as symbol sense. For example, being friendly with symbols, I will say something more about that. Having a manipulation ability, reading through symbols, engineering symbolic expressions, equivalence of expressions, that doesn't mean that equivalence of meaning, choice of appropriate symbolic representation, symbol checking and unmodeling, an ability to distinguish between roles, different roles of symbols, for example, variables and parameters. I will not tackle all of them. I chose some of these issues. I put the reference in the bottom of the slide for those of you who are curious and want to see more about some of the issues. So I chose to speak about these four, but actually the first three, as time permits. So the first one is friendliness with symbols. Here is an interesting task. You have what they call the pyramid. And what is your task? Your task is to fill in the blank cells such that here you have a 7, here you have an 8, and at the bottom you have a 42. What's the structure of this pyramid? You have to fill in the blanks. So 7 plus the number to its right should be the number behind that, and that you fill for example, if you put 7 plus 8, the number behind should be a 15, and so on and so forth. But then you have to come down to 42. And it's an interesting exercise, and most of the people I know are trying, the first issue that they're trying is a trial and error, either going down or going up from 42. And those are interesting strategies, and it's not that easy to find the right numbers. And so many people are stuck. And so even those who know algebra, it doesn't occur to them to say, okay, let's put A and B, and let's derive 7 plus A, until you go to 42, and then you will get an equation And solving the equation, you will have a solution. But when the task is not given in algebraic terms, and calling algebra in order to solve a problem, meaning that algebra is a tool that it's in your bag of resources. And many people fail to do that. Even those who learn algebra don't call upon algebra to solve problems. So one component for me on simple sense is to have the sense that symbols can help you to address, understand, and feel in situations that with numbers you may have a difficult time. So you can sense the powerfulness or the power of algebra to address situations that with other ways it's very difficult to accomplish. And the solution of this pyramid, I will not say what it is very, very surprising.
Okay.
Try it at home.
Yeah, we do.
In the paper that I mentioned, I have a different example for friendliness with symbols, but the idea is the same. If you are friend with symbols, you call upon them to solve situations that otherwise are very hard to solve. So you can have a sense of the power of symbols and why do we need them. So this is my first component of symbol sense. My second component would be reading through symbols. Usually what we see in schools is that students, even the most proficient with algebra, can do the manipulations very quickly, but most of them, they are detached from meaning or detached from their referent, and the symbols refer to numbers, for example. And having symbol sense would mean going through the symbols. What do I mean? Let me give you examples, because examples are always more illuminating than just talking. Look at this simple equation. So what students would do with subtract 5, or we subtract 4x, or whatever, or we subtract 3x, and then we find that 5 is 1x, and so on and so forth, and then I found a student, I was very surprised, I was looking at the equation and said, if I have 3x here and 4x here, what am I adding? I'm adding an x. So the 5 is the x. So that's what I'm calling reading through the symbols. Having the ability to connect to symbols before you jump to do the automatic procedures, having the sense of what they are telling to you. Here is another example. Here you have an equation, a more complicated one, and you can start developing it, and you will get an equation of degree 4, and you get into messy symbols. But reading through the symbols in this case would be, what do we have in the left-hand side? We have a fraction, x squared minus 9 and x squared plus 9. So you have a number. If subtract 9, a number which is positive. We subtract 9, because x squared is always positive, and a number you add 9. So when in the numerator, you will have always a number that is less than the number in the denominator, right? Mm. So this fraction is always less than 1. Look at the left-hand side, you have a number which is always more than 9. Less than 1, more than 9, so you can conclude that this equation has no solution. And you did it all without any manipulations, right? What I call reading through the symbols. And so that's a component of symbol sense. Here is another lovely example. This is an inequality that if you do with algebra, it can get messy because you have to consider two different cases. Mm-hmm. That the inside of the absolute value could be positive or the inside of the negative, and it's messy. Mm-hmm. But look what the meaning of absolute value is. The distance from 3 is less than 2. But distance could be this distance, or this distance. And then you have the whole solution with an I the picture. So all the numbers that are distance from 3, the distance from 3 is less than 2. So you avoid the manipulation, and it's not that I'm calling for avoiding manipulation, I'm calling for having the sense of reading through the symbols. Then you can do the manipulation, but you have something against what to contrast and control and be critical about. So that's what I mean, reading through the symbols as an important component of symbol sense. And here we come to another interesting component of equivalence of expressions and equivalence of meaning. Think of the case of the mean or the average between two numbers, A and B. What's the mean of these two numbers? A plus B over 2, right? That's the mean. That's the average. Do some elementary algebra, and you can have this A plus B over 2 is equal to A over 2 plus B over 2. If you do a meaning reading, so you say, oh, the average is composed by half the first number plus half the second number, which is a very strange definition for average. But then you have learned that from doing an algebraic manipulation that reading through one expression has a meaning that it's not necessarily equivalent to the meaning of the first expression. Here is another example. Take any odd number, square it, and then subtract 1. What can be said about the resulting numbers? Okay, you can do it with numbers. 5, 25, subtract 1, 24. You can do several examples and observe a pattern. But then if you are friendly with numbers, you would say, okay, let's model it in algebra. So if we model in algebra, this is the model. An odd number is 2n minus 1. Square it, take 1. Now work a little bit with algebra. And then you get to this expression. Then you get to this expression. And from here you come to conclude, okay, I get numbers that are multiples of 4. Right? So that's a very interesting way of attacking a very general problem. So algebra helped me generalize instead of doing many numerical examples. I can see a property of the. But now, look at what the trick I'm doing here. 4 can be written as 8 over 2. I can put the 2 on the other side, and I'm sure that n times n minus 1 can be always divided by 2 and get an integer, because one is odd and the other is even. So I can read from the expression that I can say more than they are multiples of 4. They are multiples of 8 as well, because not every multiple of 4 is a multiple of 8. So 12 is a multiple of 4, but it's not a multiple of 8. So you will never get 12 in this operation. But look, another thing, if you read through the symbols, you can see, and if you know a little bit about special kind of numbers, you can say that not all the multiples of 8 are a result, are very special multiples of 8, that the second number that multiplies is a very special number that if you know it, it's called triangular numbers and so on and so forth. So the point being here that you had a first expression, 2n minus 1 squared minus 1, and then you have a last expression in which you can derive a meaning that was not available to you in the first expression. So the expressions are equivalent because algebraically I did only legal operations. So I have two equivalent expressions, but the meaning I can extract from them could be very different. And in some expressions talk to me in a certain way, and other expression can talk to me in another way. So there you have a purpose for manipulation in order to sometimes, in some occasions, you can derive meaning that you cannot see in a different expression. So that's a point I wanted to stress that about having this idea is another characteristic of symbol sense. Choice of appropriate symbolic representations. When you have a problem and you want to model it, you can decide, you have the power to decide who is the unknown, and how do you represent the unknown. For example, let's go back to this question. And I said, okay, I represented odd numbers by 2n minus 1. But who forbids me to represent an odd number by x? I say x is representing an odd number. I restricted the set of the domain. So this is my odd number, not 2n minus 1. This is my odd number. And I can say, okay, let's square it. And then let's do it. So I have a price to pay for this representation, because here, what do I see? Okay, I see that this is a multiplication between a number minus 1 and a number plus 1. If n is odd, n minus 1 is even. If n is odd, n plus 1 is even. So I'm multiplying two even numbers. So I know this will be a multiple of 4. But I had to do much more effort than in a previous representation. Can I see that this is a multiple of 8? Yes, I can see that this is a multiple of 8 because these two even numbers are consecutive. So one of them would be a multiple of 4 and the other would be a multiple of 2. So the multiplication will be a multiple of 8. But I will never see that there are special multiples of 8. So when I model a situation, I would want to have the autonomy to represent the unknown in different ways, but then I have to be aware that this way of representation may carry consequences. This is another aspect of symbol sense. So what can we do about it? I said that there is a long list of symbol sense. So, okay, very nice, very theoretically description, very nice examples. I hope you like the examples. What can we do about it? How does symbol sense develop? Is it nature or nurture? This is people very able or capable or proficient with mathematics that do it spontaneously, because the examples I collected are all collected from students, not my invention, are collected from students. So they exist. There is an existent proof that people developed symbol sense, but could it be only for gifted students? I said no. Those for us who are in education, we don't believe that everything is God-given. So we have a lot to do in producing this, in developing this, in supporting at least certain degrees that many students would develop this kind of sense, and that's where instructions comes in. So what's the role of instruction? First of all, recognize the role of previous knowledge. Second of all, appropriate learning materials that confront the students with these ideas. And third of all, classroom practices and norms. First, legitimate the idea of staying with one exercise and looking at here in this way. Legitimize the ideas that this student had and bring them. What did you think? How do you feel it? How do you say it? And also, sometimes if it doesn't happen in the classroom, you as a teacher can model it. Oh, look what happened to me. I saw this and I saw that. What do you think? So it's a way of legitimizing and saying this is a norm that is appreciated, and you can see, and many students when you do it, they can feel that there is not only a formal, dry way of pushing around letters. There is what is the underlying knowledge? Okay, I skipped that. And what one last comment is that being competent with school algebra implies automatic actions. You want students to be automatized in certain operations because this saves time. This is, but you want them also to make sense of these automatic actions. So you want them to have an opportunistic and a flexible transition between those two, in the middle of a procedure, you want them to make sense. You want to do procedures and don't think of meaning, but at the same time you want to stop a procedure and think of what they mean. So this is a flexible transition that you want to develop, and you can do it in instruction. You can model it in instruction. You can bring them to students. So Anna Svart has a wonderful way of describing that. It's like two legs that make moving forward possible due to the fact that they are never exactly in the same place, and at the given moment one of them is ahead of the other, but they are together making the walk possible. This is a wonderful metaphor that she talks about it, and I borrow it from her about the flexible transition. Okay. I think I will stop here. I just do a little bit of promotion of a book.
Of course.
That has 4 parts. The first part is expression, the second is equation, the third is functions, and the fourth is a combination of all of them. And each of them have activities that aimed at doing exactly the walking that Anna Svart is doing, making procedural and sense-making activities combined and married together. So thank you very much.
You're welcome. And you write it in Danish, I see. So thank you very much, Arcavi. Og som jeg introducerede indledningsvis, så holder vi lige en kort pause. Vi er tilbage om 1-2 minutter. Hej så længe. Velkommen tilbage efter den korte pause. Nu vil Abraham, Arcavi og jeg have en lille samtale omkring det, han har vist på skærmen sammen med jer. And Abraham, my first question is, if you look and discuss with children around, a lot of them have some resistance to using symbols. And somehow they find it meaningless and impractical to them, and they find it very hard to understand and so on. And some of them even have math anxiety belonging to using symbols. How do we convince that this is not only for math itself, but it's for their common life and afterwards?
Oh yes, this is a phenomenon that it's widespread. Yeah. Many kids are resistant, and the idea is that it's as in every field in education. You want to teach kids not through preaching. It's important. You will see. You will need it. You will The idea to answer that question is through experiences.
Through experiences.
Through experiences.
Okay.
And my idea is that you have to choose activities in classroom, in the curriculum, in the textbooks, that will convey the sense of purpose, that algebra is doing this for some purpose, and it empowers you over situations that you can have you can understand them better, even situations that are important to you. One example that I work a lot with teachers and with students is students get, for example, a math exam, and the grades were low, and the teacher decided to adjust the grade upwards so the students will be more comfortable, and he gave a formula how to adjust the grades. So this is a situation that I want to know if the adjustment for you is more than the adjustment for me, and how will be adjusted and so on. The formula is very interesting. I don't want to go into details, but the problem that you have to get into algebra, a little bit of algebra and graphing, in order to say that the adjustment that the teacher proposed is just. So people who had a lower grade would be more compensated or less compensated, because it's not necessarily a linear adjustment. So my point being that the selection of tasks and the selection of situations should be such that the students get the feeling that by using algebra, They are empowered. There is a purpose of doing that. I gave another example of doing a trick with magic. That is, people say, "Oh, how did you do it?" Okay, let's try to. As the magicians always hide the. No, you can, if you know a little bit of math, and let's do it together. You'll see the empowerment of understanding of things. So the situations you choose, the tasks you bring to the students, should give what I called in one of the papers I wrote, purpose and empowerment. There is a study, very interesting study of curricula that was done in the United States many, many years ago, and they analyzed curriculum textbooks, and they came to the conclusion one of the categories was the algebra books provide a sense of purpose. And most of the textbooks that they graded did not provide a sense of purpose. But you don't do that by saying algebra is very important. You do it by showing situations in which you have the experience and the feeling that algebra bring you two steps forward and empowered you to understand things that you didn't understand. For example, the task of the pyramid that I show you. If you do it by algebra, you suddenly discover the structure of the pyramid and a wonderful, surprising solution that you will never have discovered if you have not the power of this absolutely magical tool.
Could there be some... I think a lot of teachers have in their mind that symbol sense is manipulating with symbols. So the children very seldom get these examples, I think. And maybe, it's not because the teacher don't want to do it, I think, but it's hard to find out. So couldn't we do something for handle the situation for the teacher? Give him examples I can use in the teacher in the education. I think maybe it miss a little. When you look at a lot of textbooks, it is manipulating. So
So the responsibility lies in two colleagues. One is teacher educators, when teachers are in the stage in which they are educated to become teachers, and curriculum developers. These two populations have the duty of not renouncing to the teaching procedures, but at the same time bringing tasks that produce this answer to the students' resistance, as you call it, to symbols.
I have another question. When I read some of your research and read your slides for today, my thought was back in the 60s and 70s. I was children at that time, and I was afterwards a teacher and having to teach my pupils the new math. And somehow I thought, we are going back to the new math, or are we having a new version of using symbols?
No, I don't think we are going back to the new math.
I hope not.
No. First of all, there are entire topics that are not taught anymore, like sets and groups and stuff like that. On the other hand, there are ideas that new math brought that stayed with us, and good that they stayed with us. For example, the centrality of the notion of function. That function is an idea of dependability between two quantities and variability and generalizability. So it's an idea that came from formal mathematics, but it can be done in a very sensitive way, the idea of function, which is so central in mathematics. So in a sense, the new math did some damage. In a sense, it left some ideas that we can take up today. We are not going back to the new math, and good that we are not going back to the new math. There was a different set of circumstances, political, educational. The United States was in a crisis because the Russians, the Soviet, all the story that we know. And mathematicians took command of developing curriculum, and of course they did it from the mathematical point of view, formal, upper university mathematics. disconnected from the needs of children. I think the ideas of symbol sense and number sense is quite the opposite. It's taking the symbols as something that you can relate to, that they have a reference, that they have a use, that they have a purpose. So it's not just the wonderful. I enjoyed very much.
We were few.
Abstract algebra. I was delighted to do exercises that don't mean anything to anybody, but it doesn't mean that this should go down to education.
Okay.
And I think that this is my answer to you.
You use the word sense, and I was wondering, could you please tell me about the connection between sense and understanding?
Yes. Yes, I say I try.
Yeah, that's what I'm talking about.
It's interesting that in English, I think in Spanish, which is my native language as well, the word sense has different senses, different meanings. So sense, the first thing is you have 5 senses. You have hearing, sight, and so on and so forth.
Yeah.
So it's something that is physiological. It's something it's in your human being that connects you to the world around you. So perceptions, so that's one meaning of sense. Another meaning of sense is meaning. It doesn't make sense to me, it makes sense to me, and so on and so forth. And there are several other meaning of senses. But when I use the word in symbol sense, I mean the meaning, but I also play with the idea that searching for that meaning should become like a sense, like something that is automatic in the same way that when you open your eyes, you see something. And you smell something even if you don't want to. So it's like having this incorporated as a physiological, intellectual, physiological, cognitive sense. So to attach meaning, to derive meaning, and in that sense, it could be tangential to understanding, but there is a problem with the word understanding because different theoretical approaches would see understanding. For me, understanding, for me to understand understanding, I would say understanding of what? So if you take about understanding the idea of function, then I can operationalize it and saying it means this, it means this, it means the seeing the dependability, it means to be able to solve this. So it's operationalize it in a sense. So talking about understanding in general may be confusing, but if you talk about understanding of a certain topic, you can be more precise about what do you mean by understanding.
Sometimes,
so in the sense they are tangential.
I understand what you're talking about. We use understanding also, I think, in very different ways. And it's very used in math because just to handle some math situation in a drilling way, it's not understanding, it's memorizing in somehow. So maybe the feeling about understanding also is an understanding.
Exactly.
Because it's very personal. When I hear what the people, when a child tell me, now I understand, I say, no, you haven't, but you feel you have understanding, and that's a very good feeling.
Yeah.
But it's the feeling of understanding,
yes,
a kind of sense.
Yes, the feeling of understanding is something very subjective. But there's 2 dangers in that. The first danger is when a student or many students, when they are successful at the procedure, they say, oh, I understand it.
Yes.
But they were successful at the procedure. So for them, the feeling of understanding was, okay, I was able to perform according to rules and get the answer that is at the end of the book. That's one danger, that the feeling of understanding subjectively, it's not what you want to call the understanding. But on the other hand, when you see a kid saying, oh, something clicked inside, something was connected, something is making sense to you, this is something very interesting, even if you know that if you give a certain task,
So
there's
would
still
show you haven't understand.
There's areas in which that are not, the idea of the field of understanding is very interesting and very important, and teachers should be nurturing it and at the same time be careful about it.
Okay, thank you very much. When you talk about symbols, you've got symbols everywhere around the children's environment, and you got it in a lot of subjects, the other subjects children have in their school time. How do you think, could there be some connection about using the simple words or making work around symbols in other subjects, and the way you handle it in a simple sense way in math? Are there some connection to other subjects in this?
Yes and no. Well, many aspects of our daily culture today is being conducted via signs. Yeah. You send a smiley face, it's a sign. In WhatsApp, you send a clapping of hands when it's something you're liking. This is a sign of something that is very directed or very transparently related to a referent. And the referent is very concrete. Or even if it's not concrete, it means you're happy, and in a sense, you're happy is a concrete thing because you know what it is. In mathematics, it's a little bit more complicated because you have ideas that you have access to them only through reference. So you construct, or some people will object to the word construct, but you get ways to talk about, and as Fard would say, about the ideas through representing them either with graphs, with letters, with conventions. So the complication of math is that you are talking about objects that you cannot see, that you cannot handle, that you cannot touch, by putting a certain language that you have to handle and understand and get to the ideas through the symbols. I think the same would happen in physics, except that in physics you have physical phenomena, and you can connect to them. You can connect to them to your senses, and then on top of that you impose mathematical symbols. But it's in a sense it's different than mathematics, that you have the idea of a group, of a function, and you only get access to them through these intermediate beasts that are the symbols and the signs.
Another question, Abraham. We were, before we are starting this session, talking about progression. As I told you, in Denmark, we have children going from first grade to ninth grade, and they could even have the same math teacher from first to ninth grade, but it's often in another way where they are changing teachers through the school years. Could we give some guidelines for a kind of progression? One of my thought was, how far do we have to go with the number sense before we are doing the sample sense? Or isn't it in that kind of order? Is it two legs going together? Could you spend a few words about the progression?
Yeah. I think Deborah Ball, who talks about knowledge for teaching, one of the components of the knowledge for teachers is mathematics at the horizon, meaning the teachers should know where the issues that I am now dealing with will become in the future. Not because he has to insert them here, but because he has to extract from the things that you do now essences that will be helpful to the student in the future, without teaching the future. So when people talk about early algebra, some people talk about teaching symbols in fourth grade. But other people, like Caroline Kieran, which her presentation I like very much, she was talking not about bringing down the algebra of 7th grade to 4th grade, but working within the number realm with meta ideas like structural thinking, for example. And the example I gave you is this and this. So putting the seeds for, in number sense, for looking through properties, using the calculations as a mirror of handling with properties. So if you instill that norm, that it goes numbers beyond the numbers themselves, without the need of bringing down symbols, you give the children an idea that mathematics is much more than doing the operations, that there are properties, that there are structures, that there are things. And if this is done day-to-day basis, they will bring that to algebra and will see algebra in a different way.
We talked sometimes of having generalized the calculation in some
yes, also.
As a kind of...
But in order to have kids generalize, you don't have to bring symbols for that. You can do generalizations verbally, for example.
That's right. Okay.
As the kid said, if I take a small number, what remains is more than if I take a large number. So you don't need you see a structure. It's a generality that you can talk with words, and that's the thing that and I like very much what Caroline was advocating.
And I think it brings to the next question. You are very concerned about the transition from procedures, to understanding. Could you use a few words? You have talked a little about it, but I think it's very important for the teachers to know how to handle these two things together and somehow.
Yes. In some mathematics education communities, this dichotomy is a big issue.
I didn't.
The dichotomy. Procedures, understanding. Procedures, understanding. What should come first? And what is more important? The discussion of what is more important is trivial because the answer is both are important. But the discussion of what should come first. I had this conversation with a Japanese math educator, a Japanese teacher, after a lesson in 2nd grade about the meaning of multiplication. A wonderful lesson in which procedures and meaning of the idea of multiplication was so well interwoven together, and it's a wonderful lesson. Then when you talk about them, procedures and understanding, the teacher said, I don't understand what you're talking about. Of course these things should be going together from the very beginning. From the very beginning, you can do activities that lead the students to be proficient in the procedure without forgetting the understanding. And this is a rich combination that favors procedures because if you understand, you can avoid certain mistakes. And and the performance of procedures feeds the understanding. So it's a thing that should be interwoven together. And again, we come back to curriculum and classroom norms and practices.
I hear sometimes people around say, you don't need to understand, you don't need to do it.
Well, it's an interesting book that I recommend very much of an American a researcher. She put PhD in history and literature in a physics course of undergraduate alongside physics students, and the ways, the attitudes of knowledge that she found was very interesting. The humanities people were very clever, didn't want to progress without having an idea of a global thing. The more scientific-oriented students were capable to live with partial understandings under the confidence that if they go working through it, it will become clearer.
Okay.
So from that is the idea of the capability of you to having the intellectual patience to see whether you can live with partial understandings in order to and one classical example is quantum physics. I heard a physicist saying once, quantum physics you don't understand, you live with it. You learn to live with it. But that's an extreme case. So it's interesting. It's interesting also this research that I mentioned because it's intellectual attitudes to our knowledge. How do and I think also Anna Sfard is advocating that sometimes you have to insist in postponing full understanding in order to undo things, in order to, but that doesn't mean that you have to separate them completely.
No. Okay. Thank you very much. Time is running, Abraham, so I will give you the last words. If you have something you have missed, you want to say for the viewers, and then we will stop the session.
No, I just want to thank you for giving me the opportunity to talk about things that I love, I can been working for them for years, and since I was a teacher myself and a teacher educator, I think I am not talking about things that are not feasible. I think that there are things that I feel, but probably people don't feel the same way, that I am with my feet on the ground. And that's the place where I come from in the Weizmann Institute. The philosophy of the department is that the theories and the research should feed into the practice, should be guide the practice, inform the practice, bring back the problematics and the dilemmas to the academia and deal with them. And I think I hope that we are in that way putting to service what academia knows how to do, and not just to publish papers, but to guide teachers as you do.
Thank you very much.
Thank you very much.
Og tak til jer derude, at I så med. Vi vender tilbage på et andet tidspunkt. Tak for i dag.